This is section 3.2, number 1. We're given a system, a linear system with a constant coefficient matrix. I'm going to call that matrix A. Step 1, we have to find the eigenvalues using the characteristic equation. Here is our characteristic equation, where lambda I is lambda times the identity matrix. Here's one matrix minus a second matrix. Here they are together. The determinant, we cross multiply this diagonal and subtract this diagonal. Since there's a 0 here, there's no contribution. Here's what our characteristic equation, polynomial looks like. Well, I didn't multiply it out, but here it is. And two real solutions. Lambda 1 is 3, lambda 2 is minus 2. Step 2, for each of these eigenvalues, we need to find corresponding eigenvectors. This takes a little bit of practice. It's an easy thing to do, but sometimes there's some interpretation that has to go on. We're looking for a vector v, so that a times v equals 3v. That would be an eigenvector for the eigenvalue of 3. So our unknown vector is xy. We multiply 2 times xy, we get 3x plus 2y, and on this side it has to be a 3x. This row times this column gives us just a minus 2y, and on this side we have a 3y. Bringing the 3x to this side, we have an equation that says 2y has to be 0. And bringing the 3y to this side, we have an equation that says 5y has to be 0. Both of these are specifying that y is 0, and there's no restriction on x whatsoever. So any value of x will make this true. And so the eigenvector for lambda 1 equals to 3 is just 1, 0. I have to have 0 for y. X could be 2, 2, 0 is a good eigenvector. There's no restriction whatsoever on x. Let's choose the simplest one of 1. Here's the check. If I multiply matrix A times 1, 0, I should get 3, 0 because the eigenvalue is 3. And sure enough, I do get 3, 0. And you can see I can factor out the 3, and A times 1, 0 is just 3 times 1, 0, and that makes sense. Let's find the second eigenvector, the one for lambda 2 is equal to minus 2. Again, we set up the same thing. We're looking for a vector v, so that a times v is minus 2v. This is our setup. We multiply row times column. We get 3x plus 2y, and here we have a minus 2 times an x. Row times column, we just have a minus 2y, and on this side we also have a minus 2y. The second equation is true for all values of x and all values of y, so it puts no restriction whatsoever on our eigenvector. The first equation, however, when we bring the minus 2x to here, we have the statement that 5x plus 2y has to be a 0, or y always has to be minus 2 halves x. So any xy pair that makes this true, any point that lies in the line where y is equal to minus 5 halves x will work. So I can choose x, and y has to be minus 5 halves x. That's one way of thinking of it. I can factor out that x and look at my vector has to be some multiple of 1 minus 5 halves. And since I can have any multiple, if I let x be a 2, I get one without fractions, which is our best choice. I could let x be minus 2. I would have a minus 2, 5, also a perfectly good eigenvector. Eigenvectors are not unique. We try to choose one where the numbers are as simple as possible. So this works, or minus 2, 5 would work. Here's my check. I multiply a by my eigenvector. I should end up with minus 2 times this eigenvector, and sure enough, I end up with a minus 4 and a 10. Row times column gives me a minus 4, row times column gives me a positive 10. Factoring out a minus 2, I see that sure enough, A times this eigenvector is just minus 2 times the eigenvector, and that's by design is what we want. Given these eigenvectors and eigenvalues, we can find two straight line solutions. The recipe for putting together a straight line solution is simply to say that the solution will be e to the eigenvalue times t multiplied by its eigenvector. And I've shown in another screencast that such a vector-valued function solves the differential equation. Well, this has two components, has an x1 and a y1 component. x1 of t is just e to the 3t, and y1 of t is just 0. Easy to graph. This goes through the point. 1. Here we are at the height of 1. And y1 of t is always 0. So that's a graph of those two functions. Part D continued. My second straight line solution includes my second eigen value and its corresponding eigenvector. This gives us a vector-valued function of x2 of t and y2 of t. I can write them this way, and here are their graphs. They both decline, they both decay to 0 because they have an e to the minus 2t in them. Part C asked us to use HPG solver to sketch the direction field and to plot the straight line solution. So here I've taken a screenshot from HPG solver, and I've laid in, so one straight line solution, and be careful, we call them lines because they do lie on a line, but they are only rays actually. They start at the origin. This one starts at the origin and moves away. This one starts at the origin and moves away. This one starts at the origin, this one would move towards the origin, and in this direction also moves towards the origin. These four separate solutions, as well as the equilibrium solution, there's technically 5 solutions indicated. Actually, there's an infinite number of solutions indicated in these pictures, but I'll say more about that in class. But what we have left to do, and the problem is not asking for this directly, is just to observe that given any initial condition, so here, for example, would be a solution. Let's actually draw it in blue. So if I were to start here, I would end up having a solution that looks something like this. Here I am at time 0, and as when time is less than 0, at -1 and -2, I would find myself in this position. There are solutions that follow these curves that do this. There are solutions that look like this and solutions that look like this. All of these blue lines can be constructed as a linear combination of these two straight line solutions, and it's an amazing fact that using two straight lines I can create something of this form or this form, this or this. Okay, that's it. Good luck.